So today's lecture is on the topic MOS inverting amplifier with push-pull configuration. So we have discussed many different configurations of inverting amplifiers. For example, in the beginning we started with this particular configuration where a P channel was used as a active load in inverting amplifier. After that we covered this configuration where a current source was used as a load, and in today's discussion we are going to have a detailed discussion about this configuration, push-pull configuration, where we are using a NMOS device here and a PMOS device. These two devices are connected in such a way that their drain together forms as output, and source of this is connected to VDD, and source of this NMOS is connected to the negative voltage or low voltage, and their inputs are connected together, and the input signal is applied to this common input. So this circuit is very much similar to the digital inverter, CMOS inverter, which we have discussed in the digital electronics part. And let's have more detailed discussion about this. So here you can see that in this push-pull configuration we have two amplifying devices. Normally in case of amplifier circuit we have one amplifying device and there is a load connected here, but here in this configuration there is no load, only two amplifying devices are there. So this M1 acts as a sinking device. We call it sinking device because one terminal of this device is connected to the most negative voltage in the circuit, and the most negative voltage in the circuit, for example, is -5 volt. This M2 is called sourcing device because one terminal of this device is connected to most positive voltage, which is VDD, and it is +5 volt, right? So now we will discuss its operation in brief. Now suppose we apply a input signal here, and for example this input signal we considered as a sinusoidal signal. Now we will see what happens during the positive half cycle and what happens during the negative half cycle. So first we will discuss the case of positive half cycle. So suppose a positive voltage is applied here during this positive half cycle, and let's consider this voltage to be 2 volt, for example. So you see here this VSS is connected to -5 volt, and here we have +2 volt. So this potential difference is very large, and this is input terminal is at higher potential as compared to source terminal. So this device is in definitely non-condition, and a large amount of current is possible through this. So this device offers very low resistance path. While if we consider this device, so here also there is a potential difference, and still you see this terminal is at lower potential as compared to this. But this potential difference is not as big as this potential difference. So this device will not offer very low resistance, or you can say as compared to M1 this device offers high resistance. So the less conductance or less current is possible through this, while in case of M1 this M1 offer very low resistance path, so high current is possible through this device. So you can say that because of the more conductance provided by this M1, so this output is pulls towards the VSS like this, and the conductance here is very less, so you can say that the output is like more towards this VSS side. And after this, let's go to the another cycle, this negative half cycle. During negative half cycle, so first we remove all this part, okay, and here you this during negative half cycle, suppose this voltage is -2 volt. So this is just as an example we have taken it as -2 volt. Now you see this volt is -2 volt. It's still, you can say, higher than -5 volt, right? So this device is conducting definitely, but if we see this situation, so here the potential difference is about 7 volt, and input terminal is 7 volt less as compared to VDD. So the gate source voltage is very high in case of this PMOS, so it will offer very low resistance path as compared to M1. So M1 will offer high resistance as compared to M2. So M1 during negative half cycle, this M1 offer high resistance and M2 offer low resistance. So it means this M1 will not provide that much conductive path, while M2 will provide highly conductive path for the current. And because of this, the output is pushed towards VDD. Because of this high conductivity path, this output will be pushed toward VDD. So you can say that it is called push-pull amplifier because during one situation when the positive half cycle was applied, that time output is pulled towards VSS, and during negative half cycle output is pushed towards VDD. So one time it's pushed and another time it is pulled toward VSS. So that's why it is called push-pull amplifier. Now, what are the uses and advantages of this kind of amplifier? So we see that the power conversion efficiency of this kind of circuit is very high, because this is class B amplifier, and we call it class B amplifier because the current flows through this amplifying device only for half cycle, and for another half cycle current flows through this device. So this kind of operation is known as class B operation. And in this class B operation, the efficiency, power conversion efficiency is very high, that is about 70%. While if we see the class A operation, where there is only one amplifying device and there is a load connected here, during in that kind of circuit, the current flows through the device during the whole or during the complete cycle. So for positive half cycle as well as for during the negative half cycle, current flow through the same device. So that is class A operation, and in that kind of circuit the power conversion efficiency is comparatively low, 30%. But here the power conversion efficiency is high, and because of this high power conversion efficiency, this kind of circuit is used as a output amplifier. Right. The reason is that the output stage of any amplifier is required to supply a sufficient amount of current to the load, and so that's why we need a circuit which has high efficiency, right? Okay, so after having this much understanding about this MOS inverting amplifier with push-pull configuration, so now we will discuss some important points. So first we will see the voltage transfer characteristics, then we will see the equivalent circuit, and the equivalent circuit is very important for any kind of electronic circuit because it helps us to find out many important performance parameters. For example, voltage gain we can find out with the equivalent circuit, input resistance we can find out, output resistance we can find out with the equivalent circuit, and frequency response also can be determined from the equivalent circuit very easily. Now let's see the voltage transfer characteristics. So the circuit is shown here, and in the circuit you see that there is most negative voltage -5 and most positive voltage +5 volt, and the voltage transfer characteristics are plotted here. You see this input is changing from -5 to +5 because input signal can change from the most negative voltage to most positive voltage. And in the same way, theoretically it is possible that the output voltage also changes from most positive to most negative, but how much signal swing is there, that depends on the input signal as well as on the working of the amplifying circuit. So in this case you see that when the input is -5, the most negative, at that time you see the potential difference between these two terminals is almost 0 in the beginning, so this device is almost in the off state, and when this is -5 and this is +5, so here the potential difference is very high, and because of that this device is highly like in the it offers very low resistance, and this output is very close to VDD. You see here it's VDD, and when we go to the other extreme, that is we apply positive voltage here. So for example, so we reach here positive 5 volt we apply, that time here we have a large potential difference, and because of that this device is in the low resistance state, it offers very high conductance, while this device offers very low conductance, or you can say this device is in the high resistance state, and because of that the output is connected almost to the VSS, and it is, you see, it's going to the very low state. And during the intermediate range of input voltages, this output voltage changes something like this. It goes from high to low like this. Now we have to see the range of input voltages for which this device is in the off state or in the saturation or in the ohmic state. So first we will see about this M1 device. So this M1 device will be in the off state for a very small range of input voltage, and you know that what is that range. So this device will remain in the off state if this gate source voltage here is less than Vt, and here in this particular example we are considering that the Vt of both devices is 0.75. Of course, for NMOS device that is plus 0.75, and for PMOS it is minus 0.75. okay, so the potential difference here should be less than 0.75. In that situation device will be in the off state. So the voltage, or the lowest voltage here is VSS. So this should be VSS plus 0.75. This Vn should be VSS plus 0.75, and after that this device will go into the on state. So for off state we can write this condition like this. If V in input voltage is less than VSS plus Vt1, and in present case this VSS is minus 5 and this is 0.75 plus, so we get minus 4.25 volt. So if input voltage is less than this voltage, then the potential difference here, this gate source voltage, is not sufficient enough to force this device to go to the on state. So if we indicate this input voltage here, so this input voltage will be somewhere here, right? So and this portion is indicated here, right? So this is 4.25. So somewhere here there is 4.5, this is 4.25. So if the input voltage from this condition, you see, if it is less than minus 4.25, means if it is less than here, somewhere here, this M1 will be in the off state. So now we have to see it is in saturation or in the ohmic. So most of the time in amplifier circuits we are interested in the saturation region. So we will see the condition for M1 to be in saturation. So you know that for device to be in saturation, most device to be in saturation, the condition is that VDS, drain source voltage, should be greater than gate source voltage minus Vt. So here for M1 this drain source voltage is V out, because this V out is measured with respect to VSS, and so V out is actually drain voltage with respect to source voltage of this device. And the gate source voltage, so here instead of VDS we write V out, and this gate source voltage, you see, gate source voltage, that is between gate and source terminal, and so we are replacing it with V in, because this input voltage is gate voltage with respect to source voltage, that is VSS. So we are replacing this VGS1 by V in, right? So this is the condition which tells us about the condition that the device will be in the saturation region. So what we have to do? So we have to find out this voltage V in minus Vt1 for different input voltages, because this condition depends on the input voltage. Input voltage varies from minus 5 to plus 5. So for different input voltages we will find out this particular condition. So here we are indicating this line. So this line indicates that when V out is equal to V in minus Vt1. So for drawing this line, what we have to do, we find out this V in minus Vt1 for different input voltages. For example, if V in is 0, at that time this is minus 0.75. So you can see at 0 this is minus 0.75. So 0 is here, is minus 0.75. If V in is say 1 volt, at that time this is 1 minus 0.75. So it is something like 0.25. So you can see that when this input voltage is 1 volt, then this is 0.25, something like this. So for different input voltages we can find out this condition and we can draw this line. So this line will act now as a boundary which will decide the voltage ranges where the device will be in the saturation. So when this output voltage is greater than this, it means when this output voltage greater than this means greater than this line, so somewhere here. So when the device is biased here in this portion, so the device M1 will be in the saturation region. So we are writing that this portion is the portion, and we can say that in this portion this M1 is in saturation, and when the output voltage is below this line, then this M1 is in the ohmic state. Now this saturation region we are highlighting with this light red color. So everywhere here M1 is in saturation. So now we move to M2 device. So first we will find out the condition for which this M2 will be in the off state, and this is PMOS device, and this device will be in the off state when the gate source voltage here is less than Vt. So this is 5 volt, this is fixed volt, so this difference will be less than Vt when this input voltage starts increasing. This voltage goes on increasing. In that case a stage may come when this difference becomes less than Vt, right? So that condition is written something like this. Okay, so when input voltage is greater than VDD minus this VT2. VT2 is the threshold voltage of this device. So this difference gives us this condition. Okay, so if input voltage is higher than this, then the device will go into the off state. For example, this input voltage here is this VDD is 5 volt, and this Vt for this device is minus 0.75. So minus we need not to consider because we are taking this modulus, so only magnitude we will consider. So 5 minus 0.75, right? So it will come something about 4.25. So it means if input here becomes more than 4.25, for example it becomes 4.3, then this difference becomes 0.7, which is less than 0.75. So this device will go in the off state, and this off M2 off will be there in this region. So this is 4.25. So if this input voltage becomes greater than 4.25, in that case this gate source voltage for this PMOS will be so low that this device will enter into the off state, right? So this M2 is off here in this region, M1 is off in this region, and between these two red blocks everywhere here M1 and M2 both are in the on state, right? So now let's see the condition for M2 to be in saturation, right? So the same condition we are writing here, drain source voltage greater than Vgs minus Vt, but here instead of writing drain source we are writing it as a source drain voltage and this source gate voltage. The reason is that source is at higher potential, right? And drain and gate both are at lower potential as compared to VDD, right? So now we can further write it like this. VSD means difference of source voltage and drain voltage. Source voltage VDD minus Vout. Vout is drain voltage. The same thing we are doing here. It is VSG, source gate voltage. So difference between source voltage VDD and gate voltage Vin, right? Like here. Now VDD and VDD they will cancel each other. So it is minus Vout. So we have to change the sign. So we change sign everywhere. So if we make it plus Vout, then we have to change this sign also, right? So this will become like this. So minus Vout will become plus Vout. So we change this sign also. Then minus Vin will become plus Vin, and minus Vt will become plus Vt. So this is the condition which decides that M2 will be in the saturation. So output voltage, if it is less than this, then the M2 will be in saturation. So same thing we will do here, what we did in case of M1. So we will determine this condition for different input voltages. For 2-3 different voltages, we will calculate this condition, and we will mark those points here, and then we will draw a straight line like this. So this straight line corresponds to this condition. So when V out is equal to V in plus Vt, V in plus Vt. So if we say that the output voltage should be less than this, it means the output voltage should be below this green line. So if output voltage is below this green line, in that case, because of this condition which is written here, M2 will be in saturation. So below this line, M2 is in saturation. Above this line, M2 is in ohmic region, right? So here M2 will be in the saturation region, right? M2 will be in saturation region, and this saturation region is indicated by this light green portion. So above this, M2 will be in ohmic region. So this is the boundary for M2, and this is boundary for M1, right? So below this, M2 is in saturation, and above this, M1 is in saturation. So that way we can say that between these two lines, so we have a limited range of voltages, input voltages or output voltages, for which both devices M1 and M2 are in saturation condition. And you know that in amplifier circuits, we prefer amplifying devices to be in saturation region. So this is the area of interest in case of push-pull configuration. So now we move to the next step. We are going to discuss now the equivalent circuit. And for this equivalent circuit, we draw a figure like this. So we have, you see here, two amplifying devices. So this device and this device. So this device, its equivalent circuit is drawn here, and for this device, its equivalent circuit is here. This is the equivalent circuit for, this is the equivalent circuit for M2, and this is equivalent circuit for M1, right? So the equivalent circuit of M2 is placed on the equivalent circuit of M1. So you see this is the output, and this equivalent circuit is very simple. You know the equivalent circuit of simple MOS device, it's almost same thing. So there is constant current source, the voltage controlled gate source voltage controlled current source, and output conductance of M1, and this is the input side, and this input voltage is connected to both. And here you see this is open circuit because no current is possible here in this device. The same thing is here, this equivalent circuit of M2. So constant current source, output conductance, drain source conductance, and input the side you see is open circuit because no input current is possible here in this. So you see this VDD is grounded because when we do AC analysis, at that time all DC circuits, DC sources are short circuited. So you see this is grounded. So this part is grounded, this bottom side is grounded. So all these grounds will they will join each other. So it means this will become this will come in parallel with this part, right? So we can redraw it like this. So this is the equivalent circuit of M1, and this is the equivalent circuit of M2, right? So this one is as it is, and this one is coming in parallel with this, right? So we have two input voltage controlled current sources and two output conductances, and now we can redraw it like this for simplicity. So the current sources are placed together, like close to each other, and these output conductances, they are placed like this, right? So there is small issue here. So in these diagrams, this current source is represented using this kind of figure, but here the current sources are represented using this different kind of symbol, but it doesn't matter. So when you use it in your notebook, you try to maintain a uniformity. So now we understand the equivalent circuit of MOS inverting amplifier using push-pull configuration, right? So we have at the output two current sources, voltage controlled current sources, and two drain source resistances or conductances. So after having this much understanding about the equivalent circuit, so we can move forward. Means with the help of this equivalent circuit we can determine many performance parameters of amplifier very easily. So first we will discuss this voltage gain, and we know the voltage gain is given by this. So this voltage gain is ratio of output voltage to input voltage, and most of the time you know that it is written like this: minus Gm into R out. Gm is transconductance of amplifying device and R out is net conductance or net resistance between the output terminal and ground, right? So but in the present amplifier circuit the situation is a little bit different. So here we have two amplifying devices, right? So we have two GM components here because both amplifying devices are contributing GM and both these GMs are contributing to the gain of the amplifier. So which GM we are going to use here, right? So it's very simple. Since we have two components and both these components are contributing, so we have to include both of them. And how? Both of them are in parallel, and you know that when conductances are in parallel they are to be added directly in order to find out the total conductance. So Gm is the total transconductance, and that Gm is actually Gm1 plus Gm2 because both these are connected parallelly, so they will be added directly. So we will replace this part like this. Instead of simply writing Gm here, we are writing Gm1 plus Gm2 and multiplied by the R out. R out, you know, is the output resistance, and if we write it in terms of conductance, then it is inverse of total conductance. So total conductance means this conductance plus this conductance. This is drain source conductance of first device M1, and this is drain source conductance of second device M2. So now in order to find out gain, what we have to do, we have to insert the value of Gm1, Gm2 and G01. G01 is actually drain source resistance. This is like actually drain source resistance offered by this device, and G02 is drain source resistance offered by this device. And from your basic understanding, you know that the equation of Gm transconductance is given by this 2k prime W by L into IDQ, and IDQ square root, and here also there is square root. So this IDQ is zero signal drain current which is flowing in this circuit here, right? ID which is flowing here, and GDS is given by this formula lambda and multiplied by the magnitude of this zero signal drain current. This is operating point current, you can say. So if you put a value of Gm and GDS here in this equation, so what we get, so this part is again repeated. So now here what we have done, so this Gm1 is replaced by this component, and Gm1 means first device M1 NMOS. So that's why, so here we have put this subscript N for NMOS and W1 L1 for this first device. And similar thing here, Gm2 is replaced by this part. So this again K prime, but we put here P because this is for this PMOS device, right? And W2 L2 both for this PMOS device. And this IDQ square root was also there, but we have taken it first, took it as a common, and then we cancelled it from here. You see in the denominator also it's GDS1 GDS2. So if you put these values here, so this ID will be same because both these devices are connected in series, so it will be taken as a common. But here you see, so this IDQ was taken as common, and in the numerator IDQ square root was taken as a common. So by mathematically we can simplify it, and here in the denominator only we will get this I square root, right? So you can see that the voltage gain now depends on these K values, lambda values, W by L values, and on the I. But you know that this K prime and lambda, they are process parameters, so they are not under the control of circuit designer. So circuit designer have control over this W and L values, and this I is also decided by the circuit designer, right? So if we want to control gain, voltage gain for push-pull configuration, and for given technology, these values K and lambda, they will be constant. So the gain will be controlled by W by L ratios of these two devices, and also by the zero signal current. So these two things, zero signal current and W and L values, are to be controlled in order to control the gain of the push-pull configuration. Now the next important parameter is input resistance. Input resistance, it's infinite, because the input side is open, it's open circuit. So input voltage is here, input current is here, so it is open circuit, because there is no current possible here in the MOS device between gate terminal and other terminals. The same thing here, because this is also in device, input device, so here also no input current is possible. So the input resistance is infinite in most of the MOSFET based amplifier circuits. And when we talk about the output resistance, you see, it's given by this. Output resistance is the parallel combination of the resistive components present here. So if we consider these components to be resistive component, then the parallel combination will be given by this. And if we treat them as a conductances, then the output resistance is inverse of total output conductance, and total output conductance will be calculated using this. So it is sum of these two conductances. And further we can solve it by putting the value of G01 and G02 from this equation, because G01 is GDS1 and G02 is GDS2. So what we will get, this lambda 1 plus lambda 2, or you can say lambda n plus lambda p brackets, and this IDQ will be common because it is same in both M1 and M2, because these devices are connected in series, so ID is common. So that way we can further simplify it to get the more accurate value of output resistance. So the next step is to discuss the frequency response of this particular configuration. So for frequency response, you know that this equivalent circuit need to be modified. So here you see, this is the equivalent circuit which we discussed in the previous slides. So but here we have added some more components, capacitive components, C2, C3 and C1. C2 between output and ground, C3 between output and input, and C1 between input and ground. So these capacitive components are added here in order to find out its frequency response. And through many discussions so far, we now know very well that the upper cut of frequency will be given by this. So C2 and C3, C2 the capacitance between output terminal and ground, C3 the component between output and input, and G2 is net output conductance, which is the sum of these two conductances. So now let's see how to find out the frequency response in case of push-pull configuration. So we write here equation for C1, C2, C3, but we are discussing only C2 and C3 because only these two are going to contribute into the upper cut of frequency calculation. So C2, you see, C2 was the capacitive components between output and ground. So we have to see what kind of capacitive components are there between output and ground. So this is output terminal. So output terminal is drain of this and drain of this. So let's consider this M1 first. So drain of this MOS is connected to ground through some capacitive components, and we remember from our device physics knowledge that drain is connected to ground through one particular capacitance, and that capacitance was, remember, that was drain bulk capacitance of first device, drain bulk capacitance of first device. And drain bulk capacitance, you know, this is a junction capacitance. So drain of this NMOS is N type and substrate is P type. So there we have this drain bulk capacitance, and this is junction capacitance, and value of this junction capacitance depends on the drain voltage, which in this case is output voltage. The same thing is applicable to this M2 device, because here also the output is drain of this device. So here again we have one capacitive component, and that capacitive component is again this is drain bulk capacitance of this second device. So you can see, so no other capacitive components are connected between this output terminal and ground in this particular case. So you see the C2, so both these are from output to ground, so they are coming in parallel. So that's why the C2 is written as this capacitive component plus this capacitive drain bulk or bulk drain capacitance of second device and bulk drain capacitance of first device. Now about C3. C3 is between output and input. So the capacitive component between output and input. And this is output and this is input. So if we go here, it's output to input. So this drain and this is gate. So between drain and gate, so from our device physics knowledge, we remember that between drain and gate there is a capacitive component, and that capacitive component, so what is the name of that capacitive component? So it is gate drain overlap capacitance. So yes, gate drain overlap capacitance, right? The same way we have a capacitive component here, gate drain overlap capacitance for this second device. So this is also like C G D. So there is not enough space here. So anyway, I am not very that much good in writing using mouse. So anyway, so this is also between output and input, and input is common. So it means these terminal of these capacitive components connected together, and these are also connected. So these two capacitive components are also coming in parallel. So you see here gate drain capacitance of first, this is gate drain capacitance of first, this is gate drain capacitance of second. These two capacitors are coming in parallel, so they are added like this. So that way we can find out C2 and C3. So now there are many things mentioned here. So anyway, so now we can find out the upper cutoff frequency, 3 decibel frequency, very easily because we have sufficient information. And this upper cutoff frequency is given something like this. So first we see that C2 is coming from here, so it is entered here like this exactly, CBD1, CBD2. Now C3 between output and input, so it is gate drain capacitance of these two devices, gate drain capacitance of these two devices. So that way we can have some idea about the upper cutoff frequency. Now one more thing remains there, and for that let's change this pointer color, and let's make it green, right? So one more capacitive component is normally connected between output and ground, which is not shown in this figure, and that is our CL, right? So this CL, and this is load capacitance, it is connected between this output terminal and ground. The CL also need to be included, and where the CL will come, it will be added into those components which are between output terminal and ground, and between output and ground we have C2, right? So if we want to include this load capacitance, and it is necessary to include it if it is present in the circuit, then it will be added here in the C2, right? So and if it is added here in the C2, it will be added in this C2 also, means it will come here also, like this. So with the inclusion of this load capacitance, we have more accurate calculation of the upper cutoff frequency. I feel that now we have covered almost all important performance parameters of MOS inverting amplifier push-pull configuration. So now it is time to summarize all our discussion. So we have discussed this circuit of push-pull configuration, MOS push-pull configuration. So we discussed its equivalent circuit, and equivalent circuit, you see we have two constant current sources, voltage input voltage dependent constant current sources, and one source is because of this, and another source is because of this, because here we have two amplifying devices. And this output conductance, one output conductance is the source drain conductance of this device, and the second component is drain source conductance of this second device. So that way we get the equivalent circuit of this push-pull MOS push-pull configuration, and from this equivalent circuit we derived many important parameters: voltage gain, input resistance, output resistance, frequency response. So voltage gain equation is given by this. The voltage gain, you see, here we have included all these things. You see, pointer is yes. So the gain for a given technology means Kn and lambda, they are constant for a given technology. So for a given technology, gain depends on W by L ratio of both these devices, and also depends on the zero signal current which is flowing through these devices. Input resistance is infinite. Then output resistance is inverse of net output conductance here, and that can further be simplified if we put the value of GDS1 here and GDS2 here, and it will be lambda n plus lambda p into ID, and we calculated frequency response also, right? So this is the equation for finding the upper cutoff frequency, right? So that way we have completed this entire discussion on the MOS inverting amplifier with push-pull configuration. So thank you very much. For further discussion, we can